Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to show you the Henderson-Hasselbalch equation and how to derive it. So let's get into this. In previous videos I've shown you how to solve for the pH of a buffer solution, and again that requires setting up your ice table and figuring out the change and things like that. But what if I told you that you could have an equation that would make the calculation a whole lot simpler? And there is an equation, and we call that the Henderson-Hasselbalch equation, and I'll show you how we get that. So first, we need to start with the general equation for a weak acid. So here we have Ha reacts with water, donates a proton to the water, gets your hydronium ion, and then you've got your leftover negative anion of the acid. So this is your conjugate base of the weak acid. And so from there, like normal, we get our acid ionization constant, and we set up our expression in terms of the aqueous solutions. So the products over the reactants, the concentration of these two, these are our products over the concentration of the reactant. And so here we have our expression. And first thing we want to do is solve this for the hydronium ion concentration, because that's pH is related to the hydronium ion concentration. So let's get that separated out. So basically we want to solve this for H3O plus concentration. So basically what we would need to do is multiply both sides by HA and then divide both sides by A minus, or A minus here. So if I take my equation, if I multiply both sides by HA, right? So then this gets multiplied by HA. So then this cancels out. And now I have concentration of HA multiplied by Ka is equal to H3O plus multiplied by A minus. So now I want H3O plus by itself, so I need to divide both sides by the A minus concentration. So A minus concentration, divide that by A minus concentration of A minus. So that cancels out. And so now I have left here HA concentration times Ka over the concentration of A minus is equal to the H3O plus concentration. And I can rewrite that. I'll just flip this around. So the H3O plus concentration is equal to Ka multiplied by this ratio here. So Ka multiplied by the ratio of HA, which is my weak acid, the concentration of the weak acid, over the conjugate, over the concentration of the conjugate base. So now that I have this concentration of H3O plus, the hydronium ion, equal to this, now I can start to get my equation from here. So let's remind ourselves a little bit that for a weak acid, because the weak acid has such a low ionization or ionization constant, it's not going to ionize as much as, say, a strong acid. So it's going to ionize a little tiny bit. And so this is the reason why the X is small approximation works a lot of the times with our acids, our weak acids, is because when they ionize, such a little amount ionizes that the equilibrium concentrations of your acid and its conjugate base are going to be practically the same as when you started initially. So the equilibrium concentrations are going to be pretty much the same as your initial concentrations. So, for example, if we say, let's say we have a buffer where in a previous problem, if you have a concentration of, let's say, acetic acid, C2H3O2, the concentration is 0.100 molar. And then the same for your acetic acid, your acetate ions, which is your conjugate base. So the C2H3O2 minus concentration is 0.100 molar. So let's say we have a buffer of those two. So since this is the acid, this is the conjugate base, this is a weak acid, the amount of H plus, or the amount of this that's going to ionize in solution is going to be so small that we can assume that these initial amounts of our species here, our acid and conjugate base, at equilibrium is going to be the same as what we have here in the initial stage here. So what we can do is then we can plug those into here. So then this becomes equal to the Ka multiplied by 1, multiplied by 0.100 molar over 0.100 molar, right? So these are equal, so that's going to cancel out. And then what you end up with is that the H3O plus concentration is equal to the Ka value. And this is true for any time you have the concentration of the acid equal to the concentration of your conjugate base in a buffer, then that's always going to be the case, that the H3O plus concentration is going to be equal to the Ka value. So you can figure out what the H3O plus concentration is going to be. Okay, so again, this would apply if the X is too small. Approximation is valid, and we're assuming it's valid because we're working with weak acids and weak bases here. So this could be the conjugate acid over the conjugate base, right? So, or it could be a base with the conjugate acid here as well. So what do we do from here now? So we have this equation here. So we've got this equation here, so that the hydronium ion concentration is equal to the Ka multiplied by your concentration of Ha, your acid, over the concentration of your conjugate base. So if we take this, let us now take the negative log of both sides and go from there. So here, I'll just continue up here. So here, I'm going to take the negative log of the H3O plus concentration, and then that's going to be equal to, and I'll take the negative log of this here. So the negative log of this whole thing, Ka, multiplied by the HA concentration over the A minus concentration. All right, so I take the negative log of both sides. Now, if we remember our rule of logs, since I have two things in here that are multiplied and I'm taking the log of both of those, then I can separate those out and it'll be the negative log of each of those. So I'll have the negative log of H3O plus is equal to the negative log of, Sorry about that, light again. So this is going to be the negative log of the Ka value, and then minus the negative log of HA concentration over the A minus concentration. So now I have this equation here. So now I have the negative logs here. So what I can do now is I can use the fact that I know that the P, the P function, like the pH, I know that the negative log of the H concentration is equal to pH. I know that the negative log of Ka is going to be pKa. So now I can substitute those. So negative log of H3O plus concentration is going to be the pH. That's going to be equal to, since negative log of Ka, that's going to be pKa. And now this here, I have the negative log of this. Now, if you remember from your log rules, if I have the negative log of this, then what I can do is I can take the ratio, I can flip this ratio, and that'll make this positive. And so I can make this the plus the log. So I made it positive, but I'm going to put the A minus concentration, the conjugate base, over the concentration of the acid. And so this, ladies and gentlemen, is the Henderson-Hasselbalch equation. So as you can see here, that in your buffer, I can put in, if I, again, assuming that the X is small approximation is valid, then I can use this equation. So because I can assume that since under these conditions, since I'm working with a weak acid conjugate base or a weak base with its conjugate acid, I can assume that the initial concentrations that I start with, is going to be the same as the equilibrium concentrations, because so little of it is going to actually ionize further at equilibrium. So if I know the initial conditions and the X is small approximation holds to be true, then what I can do is I can put the initial concentrations that I'm given for my buffer, put those in, and then figure out the pKa of the equation for the acid, and then I can figure out the pH. And so you can see here also that if the amount of conjugate base, or base, if you will, in this case it's a conjugate base, if the base is larger, if I increase the base, then this gets larger, and I'm going to add that to the pKa, and so the pH goes up, which is what we would expect for more base. And again, if I increase the amount of acid, then this gets smaller, and the log of that gets smaller. And so if I add that smaller number to the pKa, then the pH is going to be smaller or lower, which is what I would expect for increasing the acid of a base. So this is a very useful equation, very quick if the X is too small, approximation works. So I hope this is helpful. In my other videos, I'm going to show you how to use the Henderson-Hasselbalch to solve problems. Thank you for joining me. If you learned something from this video, if you like this video, please hit that like button right there. Don't forget to subscribe to my channel. The notification bell is up there. Hit that notification bell so you'll be notified by other videos I put up. And also put a comment down in the comment section. Let me know what you think, and if you've got any questions or comments for me. Thanks for joining me. Have a great day.